In this video, we're going to take a look at the second of our two light equations. This relates the energy measured in joules and the frequency of a photon of light. And they're going to be related using Planck's constant. So to review what our terms are here, okay, E is energy in joules. V, which is actually a Greek letter, it's not technically V, but it looks like a V, so we'll call it V, equals frequency. That's how frequently the light passes by a given point. And H is Planck's constant. Planck's constant is equal to 6.63 times 10 to the negative 34, and that's joules times seconds as the units. And I'll try to emphasize in a moment how we use those units to cancel out and to determine our final units for the answer of the problem. So E, energy, equals Planck's constant times frequency. Now let's look at an example. In the previous video, we related wavelength and frequency. And we determined that the frequency of this photon of light, 425 nanometers, had this frequency, 7.06 times 10 to the 14th hertz. Again, very, very frequent, a very high frequency, because we have very, very small waves moving at a very, very high speed. So these wavelengths are very, very frequent. Now we want to know then, for this frequency, what is the amount of energy per each single photon of that light, of that wavelength. So what we're going to do is we're going to take this and we're going to plug it into the equation. So we want to solve for energy. How much energy do we have here? That's going to be equal to Planck's constant, let's borrow it here, times that frequency. So here we are, we've set up the problem with Planck's constant and with our frequency. So the energy here equals 6.63 times negative 34 times 7.06 times 10 to the 14th. Multiply those numbers and you'll have your energy. Now keep in mind with the units here, I'm going to swap this out. This is the same exact number, only I've written hertz as what it, as the way that it's defined. Hertz is defined as 1 over second. And you can see here what happens is that units cancel out. In this number, we have seconds in the numerator, that cancels out. And over here, we have seconds in the denominator, so that also cancels out. So the only units we have remaining are joules, meaning that our energy, when we calculate it, will be in joules. So we multiply these two numbers, and what do we get for energy? The energy here is 4.68 times 10 to the negative 19th joules. Now that's not very much. However, keep in mind that's for one single photon of this wavelength of light. This many of those photons pass in any given second, meaning that over the course of 1 second, a given point will be absorbing many of those photons. So that's why light does carry energy, and a significant amount of energy. Even though the individual photons do not carry much energy, it adds up over the course of time, and it does make a significant impact upon its object. But all that to say, with our equation, energy equals frequency times Planck's constant. For this frequency at 425 nanometers, this is the energy for every photon of light. Keep in mind as well, remember your periodic table that you should be using. If you turn it over on the back of the periodic table, you'll find this formula in this information mid side of the page on the right. You'll see that information. Be sure to use that. Okay, everybody, do your best. Thank you very much.